Hi, and welcome to section 6.3, Applications of the Normal Distribution. In this section, we're going to be building upon what we learned in section 6.2 about the standard normal distribution and looking at some scenarios where you don't have a standard normal distribution, meaning that you don't have a mean of 0 and a standard deviation of 1. And how do we actually handle those types of situations? So let's dive in. So the key concept in this section is to present methods for working with normal distributions that are not standard. That is, the mean is not 0, or the standard deviation is not 1, or both of those things could be true. The key concept here is that we can use a simple conversion formula, and I really do mean simple, that allows us to standardize any normal distribution so that then we can use our z-score table the same way that we did in section 6.2. So let's jump into the material. So here is our conversion formula. And as we can see, it's a pretty straightforward formula. So our z equals our x, which we'll see in the problems, will be our variable, or what we're looking for. In some of the problems, it'll be given to us, and in others, that will be what we're solving for. Minus our mean, which is, again, this symbol is the symbol for a mean in this section, divided by our standard deviation. And we're told that we're going to always round z-scores to 2 decimal places. And that should make sense to us because on the z-score table, along the left-hand column, you have 2 digits. And along the top, you have an additional decimal point. And so that's where you get your 2 decimal points from, one that'll be on the left-hand side of the table and then one that will be across the top. Okay, so essentially, this is just a little pictograph showing you what we're going to be doing here in this chapter. So we're going to convert non-standard normal distributions to standard normal distributions. So again, this is our standard normal distribution on this side. So you can see our mean is at 0, and you can see that they've put a z onto here. And we're going to be able to convert to that from a non-standard, meaning that this mean is not 0. And we're going to use this formula to help us do that. So the procedure for finding areas with a non-normal or the non-standard normal distribution. So just like we did before, we're going to sketch a normal curve. We're going to label the mean and any specific x values or z values. And then we're going to shade the region representing the probability that we're looking for, whether it's to the left or to the right. And then what we're going to do is we're going to use that formula that we just saw to convert that value to a z-score. So we're going to be able to then do that conversion formula. And then we are going to use our z-score table, or technology, but in this course we're really using the z-score table, to then find that corresponding area. And as we've talked about before, area is the same thing as probability with respect to these types of graphs. Okay, so let's jump into an example. Here they don't really walk you through all the mechanics of the z-score table again and all of that because we were introduced to that in section 6.2. So we're just going to jump right in. So here's a typical type of example when you're going to do a conversion formula. So Tall Clubs International has a requirement that women be at least 70 inches tall. Given that women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches, we want to find the percentage of women who satisfy that height requirement. Okay, before we move into the next slide and start solving this problem, I want to point out a few things. In this problem, we are given 3 numbers. We're given our mean at 63.8 inches and our standard deviation at 2.6. Just based on those numbers, we can tell that this is a normal distribution, not a standard normal distribution. Because again, to meet the criteria for a standard normal distribution, your mean has to be 0 and your standard deviation has to be 1, neither of which are true in this case. We're also given one other number, this 70. So that 70 is going to represent our x. That's what we are comparing. We're using kind of as a benchmark, if you want to say. And so what we're going to be doing is saying that if 70 is that benchmark for being able to be part of the club, we want to know what percentage of women actually fulfill that based on the data that we've been given about how women's heights are normally distributed. Okay, so now that we've set the stage, let's jump into the solution for this problem. First things first, let's draw our normal distribution and we're going to shade the area. So just like we did in section 6.2, we're going to draw an x-axis. We're going to superimpose our bell-shaped curve on here, and we're going to start labeling some things. So here in the middle, we are going to label our mean. Now the mean is given to us as 63.8 inches. We're going to put that in the middle. And then we're given an x, and that x is greater than 63.8 inches, so we'll put it over here. And just like we would do before, we are able, so we're going to label everything on here. And then we're actually going to do, they have a lot of numbers here, which they haven't really shown you how to solve yet, so bear with me. Now, in this case, we don't have a z, because you don't have a z when you have a non-standard normal distribution. So we're going to use that conversion formula with the numbers that we were given to find our z. So here we go. And I wish they had shown you this prior to that previous slide, but that's okay. So we're going to convert to a z-score. So we're going to use the numbers that we were given. So again, to review, our formula is z equals x minus the mean divided by the standard deviation. So when we plug in the numbers that we were given in the problem, we find that x is 70, again, that's that benchmark for women's height, minus our mean, which was given to us as 63.8 inches, divided by our standard deviation, which was also given to us in the problem at 2.6. And when we do that math out, we find that the z-score is equal to 2.38. Now, let's go back one slide. So this 2.38 really is this mark right here, right where we had that 70 inches when we do our normalization. And so now what we're able to do is we're able to use our z-score table. So using this 2.38 that we found, we're going to consult our z-score table. It's going to be on the positive side of the z-score table, and we're going to find that the area or probability that corresponds with 2.38 is this, 0.9913. So, and again, because your z-score table always reads the area to the left. Now, for the purposes of this problem, we want to know the percentage of women that are taller or greater than this 70 inches. So we actually need the right-hand side. So just like we did in the previous section, we're going to subtract from 1, the left-hand side, so 1 minus 0.9913, to get the other side of the right-hand side, which would then be 0.0087. So coming back over here, based on all of that, the area to the right of 2.38 is 0.008656. And so we can conclude that about 0.87%, if we were to multiply this by 100 to turn it into a percentage, of all women will meet that requirement. So meaning less than 1% of women, according to this data, will be able to be part of Tall Clubs International. Okay, so just like we saw in 6.2, you can use a z-score to find a probability or an area, but you can also use a known area to then back into a z-score. And that doesn't change when you're dealing with normal distributions. It just means that, again, we're going to have to use that conversion formula to help us in this process to solve this type of problem. Okay, a couple of things that I want to point out, though, before we jump into that. So you don't want to confuse z-scores and areas. Z-scores are distances along that x-axis, and areas are regions under the curve. So those are not the same thing. Z-scores and areas are two separate things. You want to make sure that you're choosing the correct side of the graph, whether you're to the left of your z-score, which is what the table will give you automatically, or to the right, meaning that you need to then subtract from 1 your left-hand side to solve for that right-hand side. A z-score table must be, or z-score rather, must be negative whenever it's located in the left half of the normal distribution. So what I mean by that is if you're um, just like half of your table is positive and half of your table is negative, anything to the left, on the left half of your graph is always going to be negative, whereas the right side half will always be on the positive side of your z-score table. And the areas or probabilities have to be positive or zero values. They can't ever be negative. And we talked about that a little bit earlier, that actually in the last section, that the area under the curve can't be negative. It's always a positive number, or I guess it could be zero, but for the most part, it's going to be a positive number. Okay, so let's keep going. So similar to what we did in the last section, we're going to sketch our normal distribution curve, and we're going to label things on our graph appropriately. We are then going to use our conversion formula. Because again, this time we're being given the area or the probability, and we're trying to find the z-score, just like we did in 6.2. The only challenge here is that we need to do a conversion formula to take our normal distribution data and make it standard normal distribution. And so in this case, what we're actually going to be solving for is x. And that x is going to be that benchmark, kind of what we're comparing or what we're saying is the maximum height or the lowest height or whatever it may be based on the problem. And so this is actually an important formula here. This is actually the same conversion formula that we saw back here. Let me back up. It's actually this same formula, but rewritten to solve for x instead of solving for z. So definitely jot this formula down for yourself. Now, granted, you could use the other formula, but you'd have to move around the variables to be able to solve for x. And for some of us, that may be a challenge, moving around variables consistently and feeling confident that we've done it correctly. It's better to just write down this formula. So our x is going to equal our mean plus our z times our standard deviation. So again, this is just another version of the same formula. Okay, so let's jump in. So here's an example for when you're going to use a known area to then back into a z. So when designing aircraft cabins, we want to know what ceiling height, so how tall does that ceiling need to be to allow 95% of men to stand without bumping their heads. Men's heights are normally distributed with a mean of 69.5 inches and a standard deviation of 2.4 inches. Okay, so let's look at the numbers that were given in the problem. Excuse me. We're given a mean of 69.5 inches and a standard deviation of 2.4 inches. So we can tell right off the bat we're going to have to use our equation to do a conversion because our mean is not 0 and our standard deviation is not 1. Now, in the last problem, we were actually given a benchmark. We were told that our x was some height requirement for that tall women's club example. But here, we're being given something a little bit different. We're being given a percentage. So keep in mind that anytime you see a percentage, all that percentage really is a probability that's been turned into a percentage. So we're going to need to convert this percentage into a decimal so that we can then use it to find our z that we're going to plug into our equation to then solve for that maximum ceiling height that's going to allow 95% of men to stand without bumping their heads. So let's draw out just like we have in the past. So we're going to put in an x-axis, put on our curve, and then do some labeling. So our mean without the conversion is 69.5. We know that this is where our x is. We want to know what that x is. What is that height that's going to allow all of the men that fill into this area to be able to stand? And we're also given the area. That's what that 95% is. So we're going to turn that into a decimal, 0.95, and that's our area. So then using that area, if we look up 0.95 in the center of our z-score table, we're going to find that that corresponds with a z of 1.645. And we're then going to use that to solve for our x. So now that we have our z of 1.645, the mean that was given to us in the problem of 69.5, and our standard deviation of 2.4, which was also given to us in the problem, we can solve for x and find that maximum ceiling height. So again, we're going to have x equals the mean plus our z-score times our standard deviation. Sorry that the formula looks a little messed up here. Sometimes that happens with formulas when you put them into PowerPoint. So when we plug in our numbers, we're going to have 69.5, our mean, plus 1.645, our z, times our standard deviation, 2.4. And when we do out that math, we find that that maximum ceiling height to allow 95% of men to stand without bumping their heads would be 73.448 inches. So we have now solved for x using the data that we were given in the problem and the conversion formula. Okay, so just to review, when you have a normal distribution like this is a couple of little sketches, little pictorials showing you how to do this. But essentially, they're just saying the same things that we were just talking about. So we're going to make a graph, figure out what all of our numbers are, and plug them in, and then we're going to use our conversion formula to then help us solve. Okay, so that ends section 6.3 on how you deal with data that is not standard normal distribution data.